Title: Welcome to our presentation on DMPO, Dispersive Mean Flow Policy Optimization. As the title suggests, our core proposition is simple. One step is enough. We tackle the fundamental dilemma in robotic control, achieving state-of-the-art performance without sacrificing inference speed. Today, I will demonstrate how we achieve robust control at 1770 Hz on an RTX 4090 using a novel dispersive regularization technique, inference efficiency. Let me start with the key motivation. If you look at the left panel, you see a fundamental dilemma. Methods like DPPO and ReinFlow offer great performance but are too slow for real-time control, often taking 40-70 milliseconds. Conversely, fast methods like consistency policy are often unstable. DMPO sits in the upper right, breaking this trade-off. We achieve the Pareto frontier, high success rates with sub-millisecond latency. The right panel shows our approach: pre-training with dispersive MeanFlow for stable one-step generation, followed by PPO fine-tuning. Contribution. We present three key contributions. First, a unified framework for one-step control using MeanFlow. Second, a rigorous information theoretic foundation for dispersive regularization, which we found improves task success rates by 5 to 10% by preventing representation collapse. Third, a tailored RL fine-tuning method that boosts performance by over 50%, allowing us to surpass expert demonstrations. We validated this on both simulation and physical hardware, setting a new benchmark for the field. MeanFlow Policy Stage 1. In Stage 1, we process visual observations through a lightweight vision transformer and fuse them with the robot state. The critical innovation here is the dispersive loss applied to the conditional embedding. As shown in the diagram, this loss forces the representations to remain distinct in the feature space. This prevents the collapse often seen in one-step methods, ensuring the model captures the full diversity of the data distribution before any RL is applied. MeanFlow Policy Stage 2. In Stage 2, we apply PPO fine-tuning. We formulate this uniquely. We treat the environment as the outer MDP where rewards happen, and the denoising chain is simply the action parameterization. This separation makes the math clean and the training stable. Crucially, we use behavior cloning regularization to anchor the policy, preventing catastrophic forgetting while allowing us to optimize beyond the original demonstrations. Efficiency analysis. This figure drives home our efficiency. Look at the x-axis. Our method takes just 0.6 milliseconds per inference on an RTX 4090. Compare this to shortcut at 10 to 16 milliseconds or ReinFlow at 40 to 70 milliseconds. That is a 15x to 60x speedup. Ideally, you want to be in the upper left corner of this chart. High success rate and fast inference. DMPO sits exactly there on the Pareto frontier, proving we don't need to sacrifice speed for accuracy. Denoising steps. This figure answers the question, is one step really enough? Look at the green triangles for ReinFlow. At one step, performance collapses to near 60% on simple tasks like lift. It needs 32 steps to recover. Now look at our blue line. We achieve near saturated performance at just one step. This stability is directly attributable to the dispersive regularization, which keeps the representations diverse and robust even when the inference budget is minimized. Fine-tuning results. When we add RL fine-tuning, the results are striking. On the CAN task, our success rate shoots up to 100%. On transport, the hardest task, we hit 88%. This represents the over 50% boost from RL fine-tuning mentioned earlier. We match multi-step baselines while using only a single step. The Gaussian baseline struggles significantly, proving that our structured MeanFlow policy is essential for effective learning. Real-world deployment. We tested DMPO on a Franca Panda robot with a RealSense camera. On the right, compare us against MP1, which fails on lift and CAN due to representation collapse. The robot simply cannot distinguish states. In contrast, DMPO succeeds across the board: lift, can, square, and transport. Dispersive regularization makes the difference in the messy real world, allowing us to run at high frequencies with high reliability. Performance comparison. Look at the dataset column. We use the simplified dataset with only 100 trajectories, 1/3 of the full data. Yet we match or beat methods trained on the full set. On transport, we achieve 88% versus 1DP's 72%. We improve square from 35% to 83% compared to MP1. This isn't a small gain. It's a fundamental shift in capability, driven by the synergy of our three components. Architecture efficiency. Where does the speed come from? Two places: architecture and inference steps. Diffusion policy has 281 million parameters. We have just 1.78 million. That is roughly 150 times smaller. Our checkpoint is 28 megabytes versus 4.4 gigabytes. Combined with single-step inference, we achieve 1770 Hz on an RTX 4090, providing massive headroom for high-frequency control applications. Holistic radar comparison. These radar charts map performance across 8 dimensions. Look at DMPO's red polygon. It forms the outer envelope on every single dimension. Other methods might spike in speed or accuracy, but they sacrifice elsewhere. DMPO is the only method that doesn't compromise. It is the complete package, offering speed, accuracy, and representation quality simultaneously. Conclusion. To summarize, one step is enough. By synergizing the MeanFlow architecture, dispersive regularization for 5 to 10% stability gains, and RL fine-tuning for over 50% performance boosts, we have solved the efficiency-performance trade-off. We achieve state-of-the-art results with ultra-low latency. GYM pre-training results. In the appendix, we see GYM results. Pre-training beats baselines by 10 to 60%. Dispersive regularization is crucial for complex tasks like humanoid, yielding over 50% improvement. GYM pre-training. Cont. The trend holds across locomotion. MeanFlow learns robust priors, outperforming standard behavioral cloning by ensuring the policy doesn't just memorize, but generalizes. Task complexity analysis. We found a strong linear correlation, R equals 0.924, between task complexity and the optimal dispersive weight. Harder tasks like transport require stronger regularization to stay stable. Wall clock time comparison. DMPO converges much faster because each iteration needs only one step. On Kitchen Complete, we converge while DPPO is still ramping up, saving hours of training time. BC loss ablation study. Behavior cloning regularization is mandatory. Without it, the policy collapses. The BC loss acts as an anchor, enabling stable exploration during RL. Robo-mimic dataset analysis. We used the simplified dataset, 1.4 gigabytes versus 31.5 gigabytes for the full set. It preserves the trajectory complexity of the full set, ensuring our efficiency claims are valid and reproducible. D4RL dataset analysis. D4RL benchmarks show high variance in episode returns, for example, ANT, indicating significant room for RL improvement, which DMPO exploits effectively. Algorithm 1. Stage 1. Pre-training involves sampling noise, computing interpolants, and minimizing the dispersive loss. The stop gradient on the target velocity is essential for stability. Algorithm 3. Stage 2. Fine-tuning uses PPO with a linear decay on behavior cloning regularization. We start strong to preserve behavior, then gradually release to allow full RL optimization. Closing. That concludes the presentation. We hope this convinces you that DMPO is a practical, robust solution for real-world robotics. In conclusion, DMPO achieves the holy grail of robotic control, state-of-the-art performance at 1770 Hz. By combining dispersive MeanFlow with RL fine-tuning, we prove that one step is indeed enough. Thank you.